Perfect. All right, so we want to talk about 1.1 number one C, which is this thing. This thing. Okay, so I'm interested in describing geometrically whether this last thing is a line, a plane, or all of our three. They did not make explicitly obvious what the last one option was. What was the other option that this is obviously not?
Like a line?
Yeah, it could just be a point, right? It could simply be the zero vector. But in this case, I can see that I'm pretty clearly combining non-zero vectors, right? Okay, I also need a little bit of expansion of my idea of linear combination, since when I gave it to you yesterday, I said the linear combination of two vectors, right? What's the extension to 3? So if the linear combination of the first two vectors look like A times 2, 0, 0, and B times 0, 2, 2, how do I incorporate the third vector?
C times the third vector.
Yep, perfect. You guys all see that? That's a pretty natural expansion. Okay, so now let's see. So I think it's pretty clear that this first part makes a line, right? You guys see that? Okay, so my first thought is at least this stuff is a line. Now, my next question is this in here? So are the things that this second component is making, are they on the same line as the first component? Doesn't seem like it, right? So I feel pretty comfortable that I can say that these two together make a plane. And my explanation is going to be, since the first vector isn't parallel to the second. That thought process kind of makes sense? Okay, now my next question is this in here? And now the here has changed to that plane. You guys all see that? Okay, so let me think of some characteristics of that first plane, right? So I'm wondering, is there a scalar C so that C times 2, 2, 3 is an A times 2, 0, 0 plus B times 0, 2, 2? You guys see that? So that this question, right, amounts to, does there exist A, B, and C with A 2, 0, 0 plus B 0, 2, 2 equals C times 2, 2, 3? You guys see why I'm wondering that? Things in that plane are of this form. And that third thing is of this form. So I gotta wonder, is that third thing somehow in the plane? Okay, so convince me one way or the other. All.
It doesn't look like there's any scalar on either A or B that will result in C.
Yeah, it doesn't feel like it. What is it that you're looking at to clue you in there?
I'm looking at the 2's in B. If you change B at all, then both those 2's are going to change by the same amount, so you won't be able to get a 2 and a 3.
Yeah, you guys all see that? The y component is going to be 2 times b, no matter what you do. Right, so from the y's here, looking at considering the y component, and that's going to be 2b, and that's going to have to equal 2c, right? That means b and c have to be the same thing. But from the z component, I see that 2b has to equal 3c. That isn't going to happen unless unless b and c are both 0, which will also force a to be 0. You guys see that? So the only time that this vector's scalar multiples are in this plane is when they intersect at the 0 vector. You guys see that? So, yeah, not meaningfully, right? You guys see that? There exists an A, B, and a C, but it's not a meaningful A, B, and C. It's just the one time I would expect it to happen because I have a plane and a vector stuck through it. You guys with me on that? Another way you could do this is you could throw it in GeoGebra and see that they're all kind of spiky, right? That they make a caltra, that they point in 3 different directions. So my argument for this would be kind of a wordy explanation of everything I just said. You guys with that? If you go look in the book, they're kind of getting you to a sneaky thing called linear independence. So if you felt like this concept was pretty straightforward and you want a more formal definition, go look this up in the index, and that'll give you a little thing to chew on from later on that'll actually make this make formal sense. You guys good with that? Any questions on this problem?